In this video, I'm going to demonstrate the standard setup that you should use for processing Bruker.d files in AutoVectis. So first of all, start AutoVectis, and then in the splash screen, click the AutoVectis logo. The main AutoVectis user interface is split into two halves. The left-hand tabs contain the controls needed for AutoVectis to process your transient into absorption mode. And then once the file is processed, the results are shown in these right-hand tabs. AutoVectis is capable of processing these files in many different ways, but that inevitably means lots of controls, and that can look intimidating to users that don't use the program regularly. So in this video, I'm going to show you the normal setup that you would use for processing Bruker.d files. So the first thing we need to do is choose which file we're going to process. And to do that, we can use the Browse button next to the File Path control on the File and FFT tab. Bruker.d files are actually folders. And the first thing we need to do then is find the .d folder that we want to process. The file dialog here operates in the same way as any standard Windows file dialog does. So in this demo, I'm going to select this .d file and then double-click it to open the folder. Then I can select it for processing by clicking the Current Folder button down here in the bottom right. Now back in AutoVectis, we're showing the correct file in the file path. And there are relatively few other controls that you might wish to adjust while processing normal data. This is Bruker data, so we need to set the file type to Bruker. Normally for Bruker data, you would set the number of zero pads to 2, or possibly 3 if you want very high accuracy data. Remember, every zero pad doubles the effective length of the transient, and that greatly increases the memory footprint and the time it will take to process the file. Set the mass range you want by using the min and max mass controls. For this data, we don't need to go as high as 5 kilodaltons, so I can reduce that like this. Then click Enter to accept the change. If your file contains just a single spectrum, then set this control to FID. For the best resolution, set the apodization to dpac with a fraction of 0.5. The fraction control sets where the maximum of the apodization function is along the transient. A value of 0.5 means that it's at the middle of the transient, and that makes this apodization currently the same as a Han window. If you suspect your transient damps rapidly, then you can set the F value to a lower number, and I would recommend the next one to choose being 0.25. This change can increase the signal-to-noise ratio of your data, but at the expense of some resolving power. But for most data, a value of 0.5 will work just fine. Next, set this control to use ab initio values. This means that AutoVectis will use the information stored in the Bruker file to generate the first candidate phasing correction, and then it will optimize that using its built-in genetic algorithm. If you have one of the newer carts that's capable of doing 2XR mode, then it can be difficult to phase data any other way. This is because changes to the way the cart operates have resulted in a significantly increased gradient for the phase correction function, which makes it difficult to phase manually. In the unlikely event that this ab initio mode fails to produce an absorption mode spectrum, then please get back in touch with us and we can give you one-on-one training on how to use some of the more advanced phasing options. Finally, the fit order should be set to 2 because on Bruker ICR instruments the phase correction function is second order. And that's it. For the vast majority of files, these are the only controls that you'll ever need to change. And for most of these controls, AutoVectis will remember the last settings you used and will repopulate them automatically. Now all the settings are set, all we need to do to begin processing is click the Begin button. Phase correction is a process that is very much like internal mass recalibration, in that it needs a series of good peaks across the spectrum in order for the process to work. When you hit the Begin button, AutoVectis loaded and Fourier transformed the spectrum. Next, it will show this pre-phasing peak detector screen in order to help you define which peaks it should use for the phase correction operation. There are only 3 controls on this screen. This control lets you choose which way the peak detection threshold is set. For spectra with a very high peak density, choose the dense option, but for normal data, choose the sparse option. The K multiplier is very much like setting the signal to noise threshold for the peaks that you want to use, and the normal value should be 3. If you find that the peak detection threshold is either too low or too high, then you can increase or reduce this value. Finally, the low limit control lets you set a minimum value for the global threshold across the complete spectrum. For example, you may choose not to accept any peak with an absolute intensity less than 1 million. But for most normal data, a value of 0 will suffice. And you can visually view the effect of these controls in the spectrum display on the right. As with all spectral displays in AutoVectis, to rescale the graph, use these controls. In this display, the spectrum is shown in red, the threshold in white, and the detected peaks are indicated by the green points. AutoVectis will normally attempt to undertake this peak detection stage completely autonomously, so normally all you'll have to do is click Accept Peak Definitions. The phasing workflow is then completely automated. And once the process is complete, then the spectrum will be shown over here in the Phasing Results tab. You can check the quality of the phasing by looking in the Phasing Excellence tab. In this display, we can see that the phase error for all the peaks used to define the phase correction function are fairly tightly clustered around a phase angle of 0. If you don't see this, then this is a good time to ask for more assistance. But assuming that AutoVectis has successfully managed to create the absorption mode spectrum, and that would be the expected case, then the next thing to undertake will be peak picking. To start the peak picking process, we need to go back to the Phasing Results tab. On here you can choose to either detect the original magnitude mode peaks, or to detect the absorption mode peaks. And normally, you choose the absorption mode option. But whichever option you choose, it will open the AutoPeaker peak detector interface. AutoPeaker uses a novel autocorrelation-based iterative algorithm to define the peak detection threshold. This progress bar was tracking that algorithm as it completed. The only control you may want to vary on this screen is the SNR value. We'll discuss this in a little more detail in a specific AutoPeaker video. But as a general rule, you're likely to want to choose a value somewhere between 1 and 3. You can visually review where the peak detection threshold is by using this magnifying glass tool and then clicking and zooming in the graph display. Rarely, for extremely peak-dense spectra like some top-down data, you may need to set an SNR value as low as 0.1. But for dissolved organic matter data, a value between 1 and 3 is normal. And once you've identified the peak detection threshold you wish to use, then click this Accept button. Back in the main AutoVectis interface, we can now zoom into the spectrum to see the spectrum itself and the peaks that we've just picked. In this display, the absorption mode spectrum is shown in green, the magnitude mode in red, and the detected peaks by yellow centroids. So now we've processed the data to absorption mode and detected the peaks in it, and the next step now will be to export this processed data to other parts of the AutoVectis workflow. So to do that, we jump to the Spectral Info tab, and then we can export the data to AutoSeeker for top-down assignment, or to Autologous for assigning complex organic matter. And finally, for this video, if we want to export a figure of the spectrum, then we can do that back in the Phasing Results tab. So simply zoom to the part of the spectrum you wish to export in a figure, and then click Export Spectrum Figure. The exported figure will match the window size. And then to save the figure to a file, click the Save button. You can save it as a vector format PDF file or a bitmap PNG file. The aim of this video was to give you a very quick overview of the main processing steps you'd need to undertake to process Bruker data. If you want any more in-depth training about any individual one of these controls, or you want to find out about more different features in the program, then please ask for help. You can either contact us at kilgourlab.com or speak to the SpectraSwiss team directly.